We've already learned how to get a correlation matrix using the COR function in R, it comes in base R, and it works okay, but there are a couple of things that are annoying about it. We have to tell R specifically to ignore missing data. It doesn't run if any of the variables in our data frame are non-numerical, like a factor, for example, unless we tell it to ignore those variables. And it doesn't give us a statistical test of significance, which sometimes we might want for reporting purposes. So in this video, I'm going to show you a different function that comes from the LSR package called correlate. And this is a little bit more forgiving, a little bit more flexible. And so I think you'll like it a little bit more than what we've been using so far. So I've already loaded it, the package LSR, but I'll just do it again just so that it's part of the video here. So there's the LSR package, and I've already done this one as well, but we're going to use a data set from the car. And the data set we're going to use is called Anscombe. And this is the name of the researcher, statistician. And let's take a look at this data set. So we have basically all 50 states plus Washington, D.C., and we have 4 variables here. Education is the amount spent on education in that state. Income is what it sounds like, the per capita income in dollars. Young is the proportion of citizens in that state that are under 18 out of 1,000, so a higher number means more young people. And urban is out of 1,000, how many of the citizens in that state live in an urban area. So we wouldn't have to deal with any sort of complexities if we were using the core function in terms of non-numerical variables. All 4 of these variables are numerical. But if we use the correlate function, all we have to do is put in the name of the data frame. And what we get is a nice, easier to read correlation matrix here to 3 decimals, which is a lot fewer than we get with COR. So I find it easier to read. We really don't need more than 3 decimal places when looking at correlations. And you can see that most of these things are positively correlated with each other. Some of the big ones are the more that a state spends on education, the higher the income of the citizens of that state, and also that income and urban are highly correlated. So the greater proportion of citizens that live in urban areas, the higher the income is. Now, this might just be cost of living. We don't know why these things are, and we can't talk about causation, certainly. But this is nice, very easy to get. But you might want to test these for significance to see which ones are significant, if any. Now, to do that, there's a couple things that we need to do. We just redo what we did before. Now we need to just tell correlate that we want statistical tests. And so you can see in the yellow box there it says test equals false. That means that by default it's not going to run those tests. But if we instead test equals true, then it will. And then the last thing we have to do is, you'll see the last thing in the parentheses in the yellow box there is p adjust method. And we're not going to really get into this in this class, but since you're running a lot of statistical tests, because there are 6 correlations here, that's 6 statistical tests, and you can, if you choose to, adjust for the fact that you're running multiple tests so that you protect against an inflated chance of getting a false positive, a type 1 error. Now, I don't think many people do this when it's not a bad idea. But I don't think many people do this when they're reporting the significance of correlations in published articles or in presentations. So to be consistent with everybody else, I'm going to put none. Not because I think it's a bad idea to adjust to protect against type 1 error, but by default you'll see that it's going to do that using a method called Holmes method. But we're going to ask the correlate function to not do that for us, just so we're getting the baseline p-values. And when we do this, we get a fair amount more data. We see that some of these are significant. So income and education, income and urban, we already pointed those out as strong correlations. And also to a 0.05 level, we have a significant relationship between education and young. So the more young people there are in a state, the more the state tends to spend on education, which kind of makes sense. So those are the correlations themselves, and they're flagged with asterisks, so you know if they're significant. And then down here in the second table, we have the p-values for each of these correlations. Kind of like that they break the p-values out here, because a lot of other programs will put the p-values right next to the correlations themselves, and it does make the table a little harder to read. So I do kind of think that's a neat feature. And then finally, we have the sample sizes. It turns out that we have, for all of these correlations, it's based on the full set of 51 states, or 50 states plus Washington, D.C. And that's just because we have no missing data here. So there's no sort of differences in sample sizes depending on which correlation we're looking at. So that's it. That's the correlate function. Pretty easy to use. I think it's a little bit nicer than the core function. So I'd recommend using this instead of that one moving forward.